Okay, so first, just going to review the questions that were most missed on the exam. So the first one, true or false? The HR diagram graphs absolute magnitude versus spectral type. I'm not going to ask you for the answer because you all gave the wrong answer. What's on the vertical axis? What's on the horizontal axis?
It's so tricky.
It's not that it's tricky per se. I said this. We showed them that have the answer. What is luminosity? It's what? Okay. The absolute magnitude tells you the luminosity. So that's a fair answer. What I was looking for was it's the total light emitted from the star. And so her answer brings us there, since luminosity is the total light emitted from the star, and the absolute magnitude is the total light, or the magnitude you'll get at a certain distance from a star. The absolute magnitude can be calculated directly from the luminosity back and forth. So if you know the luminosity, you know the absolute magnitude. If you know the absolute magnitude, you know the luminosity. Hence, the two work either way. You could put luminosity, or you could put absolute magnitude. And so everyone missed that because I'm sure everyone knew it was luminosity and didn't think that absolute magnitude is telling you the same information. Hey, if you all missed it, that means it doesn't hurt anyone individually, because when I went through and decided how many points not to count, everybody was affected the same. And as I told you, I gave a big discount. Okay, number 2, the carbon, or CNO, I always call it CNO, cycle is a series of reactions by which, once again, no one got this right. Okay, does anybody know what it is now? Our textbook has a picture, actually, my presentation had a picture something like this, with a carbon and a hydrogen comes in, gives you, and it goes around making oxygen and nitrogen and ending up with, okay, I'm not doing this accurately. It comes around and produces a helium-4 after 4 hydrogens have been absorbed in the cycle. Now with that picture, what is it? All I heard was the intonation. I didn't hear any of the words. Okay, C, 4 hydrogen nuclei become 1 helium nucleus. That's right. The CNO cycle is not active in our sun because the sun doesn't have enough mass to create a high enough temperature and pressure to make the CNO cycle work. But in stars that have bigger mass, this is the preferred way of fusion. It's a more efficient way of fusion. It gets more energy per hydrogen. So that's what the CNO cycle is. So those two, everyone missed. I haven't graded yours.
I don't even know what I put anymore.
Okay, now ones that only one person got right. So if you got it right, feel good. True or false? Sunspots cannot be seen without using a telescope.
Let me guess.
I have to admit, I would have a problem with this one too.
Is it false? I guess the one that I didn't put because I have a feeling.
Here's all one. Good thing I'm not taking record today because everybody's excused if weather. So Mira can fall asleep because she didn't get in here because of weather. Just letting you know, I won't count against you anyway. I believe the correct answer there was false. When you look at the sun with the naked eye, you just see a bright spot. And if you keep looking at it, it'll hurt your eye. Now, real answer should be true. Why should real answer be true? You don't have to look at the sun with your naked eye to observe it without a telescope. You can take a piece of paper and put a hole in it and have that project the sun onto an object, what we call a pinhole camera, and in that you can see sunspots. So that was pretty much a bad question, I think. Anyone going to argue that? One person might get it right. Come on.
Yeah.
I was telling you the gist. Okay, next. A star with an apparent magnitude of 3 emits blank times as much energy as a star with an apparent magnitude of 5. Let's start with the easiest question. Does it emit more or less? Does 3 emit more light or less light? What'd you say?
Well, it emits more, but it also depends on the distance. That it's a lot closer.
Depends on the distance.
Of course.
If it had asked you about the absolute magnitude, then you would be able to answer. But all you can answer here is, it appears brighter from Earth. And you can tell how many times brighter it appears on Earth. But that doesn't tell you about how much energy it emits. You have to have the luminosity to know how much energy emits, which means you have to have the absolute visual magnitude. Now, let us suppose that this had said absolute. If it had said absolute, then we could calculate it. We would say the intensity B over intensity A is equal to 2.512, which is 100 raised to the 2/5 power, raised to the 5 minus 3. So we square that, and so that would be D. Yeah.
That's what I did.
So D would have been the answer if it had asked us or given us absolute visual magnitudes. All right. As a low mass protostar gradually contracts and becomes hotter, its position. Okay, so notice we have two things here. It's contracting and it's becoming hotter. So where's it going to be on the HR diagram? So once again, temp, loom. I write really not good in this direction. I know it's not great in the other direction, but that's worse, you have to admit. Which side is high temperature? So we have an object that is contracting, so it's getting smaller. What direction is radius? Does anybody remember? There's large radius, here's small radius. So it's contracting, so it's going to be moving down to the left according to the contraction. And it's becoming hotter. Well, as luck would have it, hotter is also to the left. So it's going to be going like this. And so let's go downward and toward the left. And what do you say? Now, to the left absolutely had to be true because it's hotter, getting hotter, and because radius is going down diagonally. That's why it's down to the left. Okay, two more. A main sequence star with initially more than 1.4 solar masses. What's special about 1.4 solar masses? There's a name for it.
I'm like, nope, that's definitely what.
Hopefully I spelled that right. Chandrasekhar limit. I'm still hoping I pronounce it right. I told you, Satish Moturi said that's how it's pronounced. So if I pronounce his name right, which I may not. Okay, so 1.4 solar masses is the limit for how much mass you can have in a white dwarf. Anything more, it's going to crush it. It's going to crush the electron degeneracy that's holding it up. So we have a main sequence star initially with more than that can still become a white dwarf. So it can become something with less mass than that. The question is how? How can you start with more mass and end with less mass? Stellar winds and planetary nebulae ejection can remove most of its initial mass. Let's look at the other one. Nuclear fusion uses up most of the star's initial mass. Does nuclear fusion affect the mass? The answer is yes. E equals mc squared. The luminosity is the energy per time that's being generated by converting mass. So you can calculate the mass per unit time by taking the energy per unit time divided by c squared. So it is losing mass. But the mass difference between 4 protons and 1 helium nucleus is really tiny. So in the global scheme, it doesn't matter. It's a very small fraction of its mass that it loses. It is losing mass, but very, very little. So that's why that's not the answer, because it's way too little. And then it can split into 2 smaller stars forming. Okay, that's just ridiculous. I don't think anyone answered that, because what would be the mechanism for a star to break in half? Stellar winds, well, that was the correct answer. And the last one, again, the question is misleading. Such stars cannot become white dwarfs. Well, you know they can. We said that even up to 10 solar masses can lose enough mass to get down below the Chandrasekhar limit. So the bottom one, no, it's not a misleading question. You did notice that on the preceding question, it was, right? So you have to realize that some of these questions are misleading in that they're asking you a question that you don't have enough information for. You guys know test theory. Most of the time that's not the case, because I just want to check what you know and not tricky. But every now and then, yeah, throw it in. And this is number 48. Apparently I didn't change the number. Or at least, well, there's 36, 38, 48. Maybe the last one's 36. When an object falls into a black hole, it is ripped apart by, what rips it apart? Now, none of these are fundamental. Well, actually, 2 of them are fundamental. 2 of them cover 3 of the fundamental forces. Which fundamental force is not listed there? Gravity. And gravity is the one we're worried about. Gravity's not there, which is probably why people didn't have an easy time answering it. But what is the thing that shreds it? The thing that stretches so you'd be like a mile long if you were falling into a black hole. It's the tidal force. It's the force is greater on things that are closer and weaker on things that are farther. And so the correct answer here is tidal forces, which is caused by the difference in gravitational force from one side to the other side of an object. Now the last one. Type 1 supernovae. And remember I said, there's type 1A, 1B, and 1C. And I told you at exam time, just consider type 1 to be type 1A. That's the one we've talked about. So I didn't want you to be confused and say, wait, it didn't say 1A, it said 1. So I'm going to say, just for clarity then, type 1A supernovae are produced when, and so we learned about 2 types of supernovae. There's variations, but they're basically 2 types, 1 and 2. And so name one of the 2 types, Mr. Tardy. Aren't you wearing different clothes than you were in class this morning?
Yeah, but it was too cold.
It was too cold. I had to go bundle up. And that's why I was late. Okay, what's one of the 2 types of supernovae? When do you remember?
Is it The one that exceeds the Chandrasekhar limit.
Okay? One of them is when you have a white dwarf that exceeds the Chandrasekhar limit and collapses. You had electron degeneracy was keeping it from collapsing. But if you get more than 1.4 solar masses, crunch, it forces the electrons into the nuclei and the whole thing just blows to smithereens, leaving nothing remaining. That is, by the way, our answer. That's the type 1A supernova. That's, I just wanted you to think about the type 1 to make it easy. So this here. What's the other type of supernova then? When sufficient material can be fused, it's created by... that's actually a nova. C is a nova.
Is it A?
It is A. Wait. By the helium flash in a solar mass star? No. That is what occurs when you have a star. It says solar mass because you don't have a helium flash in all stars. When you have its helium in its core and the electrons, and the pressure is such that you reach electron degeneracy before you have a high enough temperature and pressure for helium fusion. And at that point, it doesn't compress anymore. It just gets hotter and hotter and hotter. Until when fusion starts, the whole stinking core starts fusing at once. And so that's the helium flash. So that is not the collapse of a star. It's not a supernova of any type. So that's not a supernova. Not supernova. Sufficient material can be fused and created by a white dwarf as a companion star. That's also not a supernova. It's just a nova. A nova is when you have the surface of the white dwarf all of a sudden starts having fusion on the surface. So it's basically bare, big explosion, but it's on the surface. The white dwarf doesn't care. It's on the exterior, and then it just goes on, has a little more helium. And the helium flash is star 4 to 5 solar masses. Again, not a supernova. So it actually didn't matter that it said type 1, because only one answer was a supernova. The other type of supernova is the final ultimate death of a star that is more than about 3 solar masses of death. I mean, if it's bigger than the Chandrasekhar limit, it should actually have a supernova at death. But my understanding is about 3 solar masses is the limit. Oh wait, no, 3 solar masses is the upper limit for a neutron star. I got the number wrong. Just if it's more than 1.4 solar masses at death. So not a white dwarf, but more than 1.4 solar masses at death. Then you crush the core, but you have a remnant for a type 2 supernova, or a remnant that's not just gas. You either have a neutron star, that's with 3 solar masses. If it's less than 3 solar masses, you have a neutron star. More than about 3 solar masses, you'll have a black hole. Okay, those were the questions that were most missed on the test. That's why I gave you a large discount, because I thought some of those, it was reasonable that you missed them. I can understand how people have locked in their brain luminosity, and after all, that's what we put on the quiz, right? And so you didn't think, oh, that's the same thing, telling me the same information is absolute magnitude. Or the one where it gave you apparent visual magnitude, and your brain just goes to the calculation for the difference in brightness, not thinking, wait, but we don't know the distance. We can't tell about the distance, the difference in luminosity without the distance. Any questions now about the test? Oh, I should give you the test. They're sitting on my desk right now. Let me walk in and grab them. Oh, one. Sorry. Alex. Can you tell what order I have these in? You, sir, could use indexer. Okay, so there's your exam, so you can peruse and see what you got and compare. Excellent, there it is. So now we're going to talk about galaxies other than our own. So what type of galaxy, what's the name of our galaxy? The Milky Way. What type of galaxy do we call it? A spiral galaxy. So we're going to start here by looking at spiral galaxies. Now, understanding of galaxies, fairly recent. Like when we talk about astronomy, we're talking about a lot of things that were learned before Christ. But the understanding of galaxies dates back to, our textbook says, the 18th century, which means the 1700s. When, and I can't remember his name, somebody suggested that maybe some of these nebulae that people were looking at were their own cluster of stars and not part of our cluster of stars. And so we move forward to the 1920s, and Edwin Hubble, and if anyone here is like an actual baseball fan, I always think Carl Hubble, the pitcher from long before I was born. Edwin Hubble did some studies, a lot of studies. He devoted his life to studying galaxies. And as he was studying galaxies, he was, laboriously taking many hours long pictures and trying to identify galaxies. And he decided we have to have a way of classifying these galaxies by what they look like. And so he's the one that came up with all of this galaxy classification stuff we're talking about today. Now you guys have heard of Edwin Hubble, right? Because of the Hubble Space Telescope. Just like pretty soon everyone will know of Richard Webb because of the Webb Space Telescope, right? Webb Space Telescope is named after James, I think it's James T. Webb or something like that. And as far as I know, no relation. And it's not in the sky yet, so nobody knows about it except for people who take astronomy classes. So, the textbook actually has some interesting history on Edwin Hubble. It I think, makes a good 5-minute read, but it's not something I would test you on, so I'm not going to talk about his history here. But this is pictures of a spiral galaxy, another spiral galaxy. I say another, I'm pretty sure. No, I guess they're the same one, just in different spectra. Anyway, I was just concerned about that's a spiral galaxy. We can't take pictures of our own spiral galaxy. We understand we're in a spiral galaxy from the observations we can make and from seeing that there are other spiral galaxies. But we can't take pictures and see it exactly. Here's the nearest spiral galaxy to the Milky Way, the Andromeda Galaxy. So this is an actual picture of a galaxy. Now, this is not the only galaxy in this picture. If you look at this, to me, it kind of looks like a whirlpool or something here, the main galaxy. But this here, oh boy, nice choice of color. Seems like I always have that. So this here and that, those are also galaxies, but they don't look like a spiral. And so those are called a different name. They're called ellipticals. I was going to play plural in case you're wondering about the I. I changed my mind. It's an elliptical galaxy, and in fact, it's a dwarf, a dwarf elliptical galaxy. It's a small elliptical. So we're going to have another type of galaxy that's called an elliptical, and that's that type. If you look at the elliptical galaxy, how is it different from the spiral galaxy that is the Andromeda Galaxy? How does it look different? Just observation.
Looks smaller and more dense.
Okay, smaller and more dense. What is noticeably missing is a disk or arms. So the ellipticals are galaxies he saw where he didn't see any sign of a disk or arms. So how do you know, if you look edge on, you're not going to see the arms, right? So how would you know? Let's take a peek. Picture on the right. That's what you see if you look edge on. I got to turn off some more lights just to make contrast better. That's what it looks like if you look edge on for a spiral galaxy. You see the disk clearly. You see the bulge in the center pretty clearly. And actually you can see there's a lot of gas in the disk because you have that dark line going through the disk. That's because of the gas absorbing light from stars. So we know that this thing here is not the same type of object. It's a different type. Hubble figured that out. So he made specifications of the different types of galaxies. So first one, spiral galaxy. Second one, elliptical galaxy. Now, something I should point out right here is the Milky Way a large, medium, or small galaxy in your guesstimation? Okay, Alwan says a medium. Who's with Alwan? Okay, Juliet's with Alwan. Okay, Mira. Got a few people willing to put it out there. Medium is probably the best answer. The Milky Way galaxy and the Andromeda galaxy are on the large size for spiral galaxies, but they are not the largest. There are larger ones. There are more smaller ones than there are larger, but we're on the large side of medium, or the small side of large if you prefer. And I'll have a table later on that shows you the ranges in its sizes and masses for spiral galaxies. So this picture here is actually here just to remind us something that we learned. You remember Friday before we left on vacation? That we have the different pieces for a spiral galaxy. We have that bulge in the center. We have the disk that you can see clearly here. And then we have the halo that is that region above and below the disk. It actually would have been nicer to show the anatomy on the picture on the right because you can actually tell where the halo is. Picture on the left, you can't see where the halo is, right? So just a reminder of the anatomy there of a spiral galaxy. Now, tell me about the center. What's the center of our galaxy like? Okay, it has a black hole. Has like a, 3 million solar mass black hole? Something like that. It's a huge black hole. And then some spiral galaxies have a bar at the center, and some don't. Our textbook, I think, says 2/3 have a bar. And I know I've seen people speculate they all have a bar, it's just some might be so small we can't see them. So that bar is something interesting. Notice the spiral arms start at either end of the bar. So here the bar is there, and then we have the spiral arms going out. When you look at those spiral arms, what do you see color-wise? Okay, you see blue. What does blue tell you about a star? It's hot. It's massive and hot. What does that tell you about the lifetime of a star? They have a shorter lifetime. They die younger. And so that means you have a lot of fairly young stars in those spiral arms. And if I went back to the previous slide, you looked at the colors, you'd see that as well. Here's a picture of an elliptical, actually 2 ellipticals. The one, I think it's 2 different ones. Well, let's just focus on the left. It's a giant elliptical. Giant ellipticals are the most massive galaxies we've observed. You don't see any signs of a disk, right? What you have is essentially what we have in the nuclear bulge, or in the bulge of a galaxy. But this thing is huge. It's bigger, more mass than our entire Milky Way galaxy in that galaxy. But it has no disk. What's its color like? Orange. What does orange tell you about the stars? They're what? Cooler, smaller, they grow older. You can have a young red star. You can't have an old white star. And so the fact that this doesn't have white stars suggests that, they must be old enough that any white star that formed has died. So that means this must be older. Now, when I say older, we're going to come back to talk about this. There's a diagram I'm going to show you in just a few more slides. It's called the Hubble tuning fork diagram. It's what Edwin Hubble came up with for his actual classification. I have used textbooks that refused to put it in the textbook because they worry that people will take a time sequence into it. When I say this is older, it's kind of a relative term, but it's not time older, it's something else older. Notice the description: this elliptical galaxy probably originated from the collision of two spiral galaxies. We'll talk about that in galaxy formation later. Now this picture here shows the large and small Magellanic Clouds. One guess, which one's the large one? Clearly, the lower one is the large one because it's bigger than the other as observed from here. So this is the large Magellanic Cloud, the small Magellanic Cloud. Those don't look elliptical, and they don't look like spirals. So Hubble said, well, I'm just going to call these irregulars. Most of them are fitting into either the spiral or the elliptical camp. These are something different, so we're just calling them irregular galaxies. So here is the tuning fork diagram. This is basically all of the different classifications. So the handle of the tuning fork is the ellipticals. What does E0 mean? That means it has an eccentricity of 0. Now we talked about eccentricity of orbits. So what did the eccentricity of an orbit indicate to you? Right? The Earth's eccentricity as it orbits around the sun. Indicated a lot. The eccentricity is a measurement of how close to a circle it is. An eccentricity of 0 meant that it was a perfect circle. Eccentricity of 1 would be a line where it's just going back and forth like this. Eccentricity for a sphere is the same idea, except for you are rotating that shape. So an eccentricity of 0 means it's spherical in shape. An eccentricity of, 9, these numbers here are multiplied by 10. So an eccentricity of 7 would be 0.7 for its actual eccentricity. Right, the E7 is 0.7 eccentricity. And if you get out to 1, that would be a straight line. So 7 is about as high as it goes. So 0.7 is the eccentricity there. So it's just telling you how elongated the sphere, or the ellipse is now. And then we have, sorry, that doesn't fit, so I'm erasing it. Then we have two branches on the tuning fork. The reason he made it into a tuning fork shape was because you have the same type of variation whether you have a bar visible or not visible. And so he noticed that some of the spiral galaxies had a very tight winding to the arms, and some had a very loose winding. And so the ones with really tight windings he called A, the ones with very loose winding he called C, and the ones in between, which is where both we and the Andromeda Galaxy fall, called B. And so the upper arm is spiral A, spiral B, and spiral C. And like I said, our Milky Way galaxy is a spiral B. Now, what would make it wrap tighter or not as tight? What pulls things in? Gravity. And so it does turn out like it would seem. The ones that have the arms pulled in tight have more gravity pulling them in. And what makes gravity stronger? More mass. So the A types, S sub A, has a more massive nuclear bulge. More mass in there in the center. And so it pulls the arms in tighter. And you get out to C, it's the least mass in the nuclear bulge. Or I call it nuclear bulge. I hope nuclear is the correct term in this case. And then you have the same things in the barred. So you have a spiral barred sub A with a very massive bulge. B, not as massive. C, least massive. So this is purely a classification diagram. Like I said, I've seen textbooks that don't even show this because they're worried that people will think it's a time progression, that over time you move from this point to this point to this point. And it's not. It's just a classification. It's kind of like a classification for cars. This is a compact that runs on gasoline. You know, this is a sports car that runs on gasoline. This is a compact that runs on diesel. Over time, it's not going to change. These do change over time, but not because of aging, not because of how much time has passed. Let me just cover that base now because I've now alluded to it twice. In observing galaxy clusters, we have clusters of galaxies. In observing galaxy clusters, some clusters don't have that many galaxies. And so if you don't have that many galaxies, you're not going to have that many collisions between galaxies, a logical conclusion. Some galaxies are very rich. They have lots of galaxies in them. If you have lots of galaxies in your cluster, you're going to expect a lot of collisions. Well, the galaxies that don't have many collisions, they're mostly irregulars and spirals. The ones that have lots of collisions are mostly ellipticals. It doesn't matter how old the galaxy is, or the galaxy clusters are. It's how many galaxies are in the cluster. So the conclusion is that it's not an aging sequence, but it's a collisional sequence. You start basically with clouds of gas. Shock waves make stars. Well, what causes shock waves? Here's something that causes a big shock wave, when two clouds of gas hit each other. So if you have two galaxies that come and hit each other, you're going to create shock waves, which is going to cause both of those galaxies to have an enormous burst of stars. And so when you have this enormous burst of stars, what happens? Well, the amount of gas you have available decreases. And so every time you have a collision, you have a whole bunch more stars made and less gas available. Until eventually you get to the point where you've basically run out of gas to make new stars with. At that point, you're not going to have the disk or anything anymore. Because the disk is where you have shock waves basically anchored by that black hole in the center going around in circles. And the shock waves are creating stars as they go through. So they're basically, think of it like a sprinkler going around like this, creating stars every time the shock wave comes through a place. And that's where we see the spiral arms, is where the shock waves are, because what we're seeing is the bright young stars, the ones that don't have long lives. Hence me pointing out earlier that the spiral arms were blue in color. Now, some characteristics of the different types of galaxies. So we have the three types: the irregulars, the spirals, and the ellipticals. And if you look at the mass, the type of galaxy that can have the most massive galaxy is the elliptical. Goes up to what, 10 to the 13th solar masses? Spirals go up to only 10 to the 12th or so. Our galaxy is somewhere around, I think, around 10 to the 11th. So we're on the higher end of the spiral galaxy mass, but not at the top. So ellipticals can go the highest, but also ellipticals have the lowest total mass as well. Around 10 to the 5th, and 10 to the 5th, that's 100,000. About 100,000 solar masses in some ellipticals. Those really small ones are called dwarf ellipticals. The really large ellipticals are called giant ellipticals. Scientists are really crazy with these naming routines sometimes. Irregulars, well, the irregular ones are kind of centrist in mass. Then if we look at the size, ellipticals, you see those giant ellipticals greater than 700,000 light years across. Those are your biggest galaxies you can make, is the giants. Most massive and the biggest. The spirals tend to be large, the irregulars tend to be small. Luminosity, though, the spirals are actually, I know this has the same number, but the spirals are the most luminous of the galaxy types. By the way, the dwarf ellipticals were discovered fairly recently because they don't give off much light. And they're now believed to be just like when you look at the stars. Remember we talked about the number of stars by spectral class, and the ones that have the most stars are M's, the low mass stars. Same thing here. It's believed that the small, the dwarf ellipticals are probably the dominant type of galaxy in the universe, but they're much harder to observe because they don't give off as much light as the others. Populations, spirals, and irregulars have both old and young stars. Both old and young means they've been around for a while, so they have old stars. Young stars because they're forming new stars. Whereas the ellipticals aren't forming new stars. They've run out of gas to make new stars, so they're just old stars. The line just below is basically the Y of the line above. Why do you have no new stars? Because you have almost no dust and little gas in the elliptical. Whereas if you look at the irregulars and spirals, you have gas and dust. The irregulars have lots more gas and dust because they probably are pristine. They probably never had a collision if they're still in the irregular form. Once you've had a collision, you're going to shift into the spiral form. So irregulars are unbesmirched. Then we have the mass to light ratio. And this one here takes a little explanation. Why would mass to light ratio matter? By definition, the one for comparison here is the luminosity of the sun divided by the mass of the sun. And so this is based on the sun. If you have a smaller star, its luminosity drops as radius squared. And so even though the mass drops as radius cubed, so if you have less mass, the mass to luminosity ratio becomes bigger. So low mass stars, ones that can live a long time, are going to have a bigger mass to luminosity ratio. And so you look at these numbers and they're telling you basically what's the typical size or typical mass, same thing, right, of stars in this type of galaxy. And so you see 1 to 10 here. 1 is the lowest number on this. That means it's the one that has the biggest average size for stars. This one here, 2 to 10, very similar but slightly smaller masses per stars. This one here, 10 to 20, much less mass per star. So less mass per star, stars that live longer lives. Doesn't have any bright young stars. That's what that tells you, basically. And yeah, that pretty much finishes that one. Now we're heading into what made Edwin Hubble super famous. And that is, in his study of galaxies, he determined ways of measuring how far away a galaxy was. Now, our textbook points out before Hubble, published in a fairly obscure Belgian journal, that it appeared that most galaxies are moving away from us. So you will have people argue that Hubble must have read Lemaitre's paper. Very few people talk about it because it was an obscure journal, and that all of his findings are based on Lemaitre. I don't care. I care about the outcome. Edwin Hubble is famous for this, and he did do a lot of work, whether his idea was original to him or whether he got an idea from Lemaitre and then ran with it, is the argument. So these things that are listed on the left are methods of determining how far away something is. So we have the planetary nebulae. Planetary nebulae, remember that is the nebula, the gas, that's been emitted by a star before it dies and becomes a white dwarf. Those are typically about the same brightness. So if you can find a planetary nebula and you measure, I said they're about the same brightness, they're about the same luminosity. You find a planetary nebula and you measure its brightness, and if you know its luminosity, then you can calculate the distance using our difference between absolute and apparent visual magnitude equation. So that's the first method, and that works for stars within 70 million light years. Then we have Cepheid variables, the things that Harlow Shapley used in studying the globular clusters, determining approximately how far away the center of the Milky Way galaxy was and where it was, even though his distance was wrong because the calibration for Cepheid variables wasn't done very well at that time. The Cepheid variables, the luminosity of a Cepheid variable is dependent on its mass. And so, its frequency is tied to its luminosity. Of course, luminosity depends on the mass. So you can determine by looking at the frequency what the actual luminosity of the star is for a Cepheid variable. And then knowing this luminosity, and once again measuring its brightness, you can use that distance equation to calculate its distance. That goes out to about 110 million light years away. That's as far as Edwin Hubble had to work with. These other things, well, yeah, the Tully-Fisher relation is actually really interesting. You have galaxies that are spiral galaxies. We talked about mass. The more mass it has, the tighter it's going to be wound. Well, also, the more mass it has, the quicker it's going to rotate. And so if you can measure the rotation rate of a galaxy, you can approximate of a spiral galaxy, you can approximate its mass. If you know the approximate mass of the galaxy, you know its approximate luminosity. And so since galaxies give off a lot more light than stars, that allows you to go further out. Not that much further out. Then you have the type 1a supernovae, as we just talked about in reviewing the test. Those are 1.4 solar mass, white dwarfs, that suddenly get enough mass to collapse and erupt in a bright flash. That bright flash is very reproducible. And so if you find a type 1a supernova, you can, again, you know the luminosity, measure its brightness, and you calculate the distance. And that goes way out there. It's 11 billion light years away. 11 billion light years? The age of the universe is believed to be 13.82 billion years. So that's going essentially all the way back. This last one, Rev's Hubble's law, that's the one that goes all the way back, but of course Hubble couldn't use that. That's what Hubble came up with. So he took the distance measurements from the first two things, and he made this graph on the left in 1929. So this is plotting how fast galaxies are or objects are moving away from us against how far away they actually are. And he found that there's approximately a straight line relationship. And so now if you look at his original data there, it's not a really tight fit. I mean, you would look at it and say, yeah, I see an upward trend. That's not a good fit. 2 years later, working along with Humason, which, once again, read your textbook. It's a really interesting story about him. He dropped out of school in 8th grade and was running a wagon up and down to a telescope so that he could be involved with astronomy. Eventually, he was working with Hubble. So they produced this second graph that goes much further distances because they were able to use another relationship to get distances. And now you see a much stronger linearity. So now the outcome of this is you have a straight line relationship. Remember, oh, I am totally out of time. I'm totally out of time. I'm going to stop here instead of taking more time. I'm sorry. I didn't realize time had gotten away from us. So I will pick up on